let's just dive into why people should use Kubernetes and how. And if anybody has any questions about myself, we can go over that in the end if there are no better questions. So yeah, this is scientific computing with Kubernetes, and let's go into it. So before we go to Kubernetes, I want to set the stage. So the reason we are even talking about Kubernetes is because Kubernetes containers have become the norm in scientific computing. It helps with code portability, and as you know, most codes have lots of dependencies, and bare metal is just not an option. And containers are definitely faster than virtual machines. Just remember they are stateless, so unlike virtual machine where all the state is preserved, when the container is gone, all its state is gone. Now, most of science doesn't live with just one container, one job on one machine. We typically have lots of compute going on in different containers, and we usually want to use lots of nodes too. So once you have lots of machines, lots of containers and lots of machines, you need to somehow manage the whole, and this is usually referred to as orchestration. And Kubernetes labels itself as production-grade container orchestration, so it seems like a perfect match. Now, what is Kubernetes, or KTS? Although KTS is usually how you write it, but hardly ever pronounce it. So I'll keep talking about Kubernetes, but you may see me write it KTS because it's just easier. It was originally created by Google, but it's now maintained by the Cloud Native Computing Federation, and I have a link there. It's open source with a very large and active development community, and it can be deployed both on-prem and in the clouds. So several of the NSF-funded clusters are on-prem, but you can go in most of the commercial clouds and spawn your own cluster there. Certainly in Google, but also in AWS, Azure, Oracle, just to name a few. So that's Kubernetes. Let's now see how do we use Kubernetes to manage our containers. But before we go to that, let me make it clear that Kubernetes actually doesn't manage containers on its own. It always talks about pods, where pod, it's really just a set of containers. So when you talk to Kubernetes, you talk about pods. Pods are a set of containers. It's fine to have just one container per pod, but it still needs to be inside the pod. Why this? Well, because there are some convenience when you pack together several containers. They can talk to each other, they can exchange state. You can have different things running in different containers in isolation, and some people think that's useful. So that, like it or hate it, that's how it is. Now, when you have containers, you need to have some container image. There is no default container in Kubernetes. You have to pick one, and you can mix and match different containers inside the same pod if you run multi-container pods, but each one must have one. Where do images come from? Well, you have to fetch them from somewhere. It will not come from your, let's call it submit machine. It has to come from a repo that is external to your Kubernetes installation. By default, this is Docker Hub, but most setups can fetch it pretty much from any Docker compliant repo too. And while pods on their own are useful, they have some limitations. When they are gone. So if anything bad happens, nobody will do a restart for you. And here is where jobs come into play. There is a notion of jobs inside Kubernetes, which essentially is a set of pods, and the job, it's called a controller, will make sure that the pod will run to completion and it can even restart it if it exits with a non-zero exit code, which can be useful to make sure that things work and you get the result out. If you have some transit problems or something like that. It can even help you to run parameter sweeps. You just tell it to run a certain number of, let's call them tasks, and it will create one pod for each of them and make sure that all of them run to completion with a single submit. So that's very similar to what you would expect from a, let's say, traditional batch system. Now that's just containers, but most jobs need some specialization. You don't want to create a container image for each and every job you run. It's better to have a single image and then pass in all the configuration you need to customize the job you're running. And Kubernetes provides easy mechanisms to inject several kinds of information inside the container image at runtime. And there are really three mechanisms. There are config maps, secrets, and environment variables. The config maps are essentially a collection of files. You create a config map ahead of time, populate it with any number of files you want, and then when you're ready to launch a job or a pod, you can mount any of those files inside the container in any location you want, literally any location you want. And if you have a lot of files, you can even mount the whole config map as a directory structure inside the config map, which is very handy. Just one clarification, while it is called config maps, you are not limited to config files only. It's really just files. So a config map can contain your main executable and libraries on top of any configuration if you want. Scripts, whatever you want, it's just files. So it's really flexible and allows you to customize your container at runtime completely. As I said, there is something called secrets too, which is very similar to a config map, but adds a few more protections on who can see what's inside. So it is suitable for things like passwords and tokens, which you need a little more protection from. Until they are mounted in a container, they are essentially encrypted and nobody can access them. But the moment they are mounted in the container, they behave pretty much just the same as a config map. So yes, it adds a little bit of protection, but it's not a silver bullet. So just to make it clear. And finally, the environment variables. You can inject any environment variable you want with any value in the runtime of any container you own. And they're easy because you don't need to create an object like you have to do with config map. You just specify the environment variable name and value at pod launch time, and it will show up when the process starts inside the container. So they are very easy to use, and they're often used in conjunction with config maps. So you have complex logic in config maps, and you steer it by adding environment variables at runtime. So how about your work area or ephemeral storage? Well, there is all the directory structure that came with the image. In most systems, anything that came in the image, it's writable. You can read and write any of the files that were already there. You can add files in the same directories. You can create new directories. So that's one avenue. However, sometimes that's either too small or too slow. So Kubernetes has the option to mount additional temporary work areas or ephemeral storage inside the container. It can be at any mount point you want. And that's typically way faster and can be bigger. It's known as an empty dir. in Kubernetes speak. So if you, I have a link down there. There are the slides, you can look at it. But else it looks and feels like any other directory. And of course, you always have the RAM disk, as with all Linux systems. Unfortunately, by default, the depth shared memory in a container is pretty small. I think the default is 64 megs, which is not much these days. So if you want a larger one, you essentially need to map an empty dir on it, and to make it fast, you can tell the system that that is memory-based empty dir. Now that you're not required to map it on depth shared memory, it could be mapped somewhere else, but mapping it to depth shared memory, it's a typical use case. Now, that was the work area inside the container, but work area ephemeral storage means the moment the pod has finished, that area is gone. It's deleted. You have nothing left to show for, which is probably not something you want. You probably want some kind of persistent storage. And Kubernetes provides several hooks to interface with persistent storage. Typically, it will be a remote file system like NFS or Ceph. For more adventurous users, you may import block storage, which essentially shows up as a block device inside the container, and you can format it with your favorite file system, or even use it raw if you use a database, for example. It's a set for adventurous users. There is always local storage, which is typically ephemeral, but for some applications, it may be possible to configure your local storage that will persist across pod invocations. For example, if you have a node-locked service that needs to be really fast, that's an option to go, but will severely limit you in what you can do because you cannot move that storage between nodes. So really for advanced users. And if none of that is good enough, you can always the option of direct access to external services, which is not managed by Kubernetes, but you can always do it. So you can use the S3 protocol, HTTP protocol, Globus, SCP, whatever you like, and move data in and out of pod. For what is managed by Kubernetes, how do you do it? You will need to pick the volume to mount. That's what it's called, volume in Kubernetes pip. You may be able to create it at pod creation time, but typically you will pick one that already exists, and it's called persistent volume claims. So when you want persistent storage, you would usually look for a PVC that already exists, and then mount it inside the container. And like with the config map, you are free to mount it wherever you want, whatever works for you. And that's all I have for the concept of a pod, of a job. Let's spend a couple of minutes talking about how do you schedule pods, because you probably want your pod to run somewhere, right? Now, Kubernetes comes with a matchmaking scheduler. If you're familiar with HT Condor, the concept is very similar. Nodes advertise what's available, pods specify what they require, and Kubernetes does the magic and finds a resource for the needs that the pod has. There is also a notion of priorities, which is convenient for opportunistic use. We use it a lot in OSG when we don't have high priority users. We always have a lot of low priority jobs in the queue that will only use resources that high priority users don't use. The moment the high priority user comes in with a pod that is needed, the low priority pod will be preempted. Not sure you will ever need to use it explicitly, but it's good to know it's there. And that's all I have for the high level concepts. Let me now spend a few more minutes looking at how you actually use Kubernetes using the concepts I introduced so far. So There are several ways to interface with Kubernetes. Most users will end up using the kubectl tool, which allows you to do anything that is possible to do with Kubernetes. You could create the jobs, list them, change them, delete them, and much more, as we'll see. And what is kubectl? Well, it's just a static library, single file. You can download it there. It's available for all the major platforms. And the idea is that you install it on your laptop, no dependencies whatsoever, single file, and interface with your Kubernetes cluster anywhere in the world, assuming it's properly configured. All you need is a config file, which will be specific to the cluster you want to access. But apart from that, really, you need two files: the kubectl executable and the config file, and that's all you will need to be able to interface with the Kubernetes system. This assumes that the config file doesn't use some fancy authentication mechanisms that require other tools, but that's beyond pure Kubernetes. It's really specific to the provider you're interfacing with. Now, you know the tool, but what do you pass to the tool? So if you look here, I said, yeah, it's always a file name. So that file name will be most likely formatted in YAML. And this is true for both creating and configuring pods and jobs and storage and a lot of other stuff. But you also get YAML documents back if you want to get a detailed description of jobs or whatever you're interested in. Although there are more simplified human readable formats with less information, but if you want the gory detail, YAML is the way. Now, if you never heard of YAML, don't be scared. It's actually quite easy to use. There is a reason why it describes itself as a human-friendly markup language. I'll have an example in the next slide. I just want to stress one detail that often trips newbies. It's that it uses Python-like indentation to indicate nesting. So if you're used with Python, it's probably pretty natural. If you haven't, well, it's time to learn. So here is an example of a YAML, a simple YAML document. It is very simple. Anything you will ever do with YAML will be orders of magnitude longer. If you look at it, it's actually not complicated to parse, but it's very pedantic. So be prepared to lots and lots of lines of code and proper indentation. Once you get the hang of it, it's not a big deal, but it's definitely not something very compact. So this is just an example, and I'll go over a few YAML examples of real things you would do with Kubernetes, and I'll try to keep it as simple as I can. So here is a simple YAML that it's actually functional and will launch a pod. So first thing to notice is that you must pick a unique name. Unlike most batch systems, you don't get just the next number. If you use the Slurm or htcondor, you don't specify the job name. You specify the definition of the job, you submit it, and you get that identifier. Here, you have to provide the identifier, and it has to be different every single time you submit a new job, unless you delete the previous one. So this is a difference between the traditional batch systems and Kubernetes. Love it or hate it, that's how it is. Next, you have to specify the container image to use. As I said, no defaults, so you have to pick one. It can be just a base operating system image like here, but most likely you will have a more customized one that has all the tools and libraries that you need for your application. And finally, you specify what to launch. While that's optional, the container image may have the default process that will be launched. In my experience, for most scientific applications, you do want to specify what you want to run, so you can provide the necessary arguments to personalize it. Oh, actually, just remember, I haven't mentioned that you can pass arguments. So that's another thing that is similar to the environment variables, but goes straight into the execution line that you launch. So, oh yeah, if you see here, what I did here was just run sleep. So this one will do nothing, and it's a good way to start an interactive pod. And this is what you would do. You would create the YAML, you would launch it, check until it started. It may take a few seconds to a few minutes, depending how busy your cluster is. And at that point, you can log into it with kubectl exec, do whatever you need with it, and after you're done, you delete it. So this example would work as it is. Probably not the most feature complete example, but it will work. However, that's just the beginning. Launching the pod, it's the first step, but as I already mentioned, you probably want to see what's going on with it. So kubectl get pods is what gets you the list of all the pods that are currently submitted, and it tells you in what state it is. Is it depending? Is it running? Is it finished? I like to use the -o wide option, which provides you a little more detail, but that's optional. One thing of note is that jobs and pods are two different concepts in Kubernetes. So when you do kubectl get pods, you don't get the jobs. So if you want to go get the jobs, you need to do kubectl get jobs. However, the jobs just give you the logical job, and the job is actually launching the pods on your behalf. So actually, kubectl get pods is what you will use most of the time, but you need both. And for when you are exploring storage options, kubectl get PVC is probably the tool you will want to use. And when things don't go right, so you keep doing kubectl get jobs and the job never starts, something may have gone wrong. So you can look at events to see what's going on. So kubectl get events tells you what Kubernetes is doing about your pod. Just one note, the ordering is a little funky. So I really recommend that you sort it by time. So that's the magic line, not short at all, but after you have it somewhere to cut and paste, it's not too bad. And I already mentioned that you can log into a pod, which is mostly useful for debugging. If something goes wrong, your pod was supposed to run 10 minutes, but it has been 2 hours. You can log into any pod you own and poke around, pretty much like with SSH. As I said, most useful for debugging, but it's actually a great tool for interactive computing too. So that's for the basic pods, but we mentioned before that's not enough. Most jobs will not be just sleeper jobs that you want to interactively log in. You actually want to configure it. So how we do it? So let's start with config maps. Here on the left, you have the command you would use to create a config map with 2 files in it. As you see, again, not very short, but pretty simple. And then inside the YAML, you have 2 places to do. You first need to tell it which config map to use and which files to get out of it, and then you tell it where to mount it. Again, not hard, but very pedantic. And after you have that, you can use it. In this case, this is actually the script we want to run. So we mount the code we want to run and run with it. So this should be pretty familiar with a lot of people who do scientific computing in the batch world. Now, assuming that our script wants to be configured and it does that through an environment variable, you can inject that by adding this couple of lines. So I said I want to define an environment variable with the name p steps and give it a value of 100,000, and it will appear in the environment variable of this command. And then how this command uses it is beyond the scope of Kubernetes. Hopefully the code in there is right. You provided it, right? And an example of storage. As you see, it's very similar to what you did in the config map. You tell Kubernetes where to get the storage from, and this is the persistent volume claim line. You tell it, get the PVC with this name and mount it at this location. Once you do it, Kubernetes will do it, and now you can use it. In this example, my executable was on the persistent storage, and my data was on this persistent storage. So everything runs from this existing persistent storage that Kubernetes had mounted inside my pod. Kubernetes has no idea what it is, but it will do what you asked him for. And now let's spend a few more minutes on the matchmaking. And I had already the requirements in my first example. I just skimmed over them. They are needed. You need to provide a requirement for each and every pod, because Kubernetes needs to know what you need to run your application. Some clusters may have defaults, but don't count on them. So make sure you always request what you need. In this case, I require 1 CPU, 12 gigs of memory, and 1 GPU, and I want it to be either an A100 or an A10. Now, one thing to understand is that requirements are hard requirements. Your pod will not start unless Kubernetes can find those resources. So make sure you request only what you need, because if that's not available, your pod will simply not start. Which, if you need it, you need it. Better not start than fail because you don't have what you need. But sometimes you just have preferences. In this case, I say, okay, I need a GPU, but I would really prefer the fast one. If at all possible, don't pick this two. But if that's the only thing that's available, if you use prefer during scheduling, it will still give it to you. So the idea being better to run slow than not start at all. So if it is optional, mark it as optional, but if it is required, mark it as required. Finally, there is also a concept of limits, which typically you set them higher than the request. The idea being that you should request what you expect you will need, but give yourself a little bit of wiggle room. If you miscalculated what you need, you give yourself a little bit of breathing space so your job is not killed if it goes slightly above what you requested. But if it goes significantly over that, just kill the job, because it means something went really wrong. So you want to protect the system while still giving you a little bit of breathing room. And since most applications don't really use everything they request, as long as the difference between this and this is not really big, the system will work perfectly fine. One thing to notice is that memory is a hard requirement. It's a hard limit. If you exceed it, you will simply be killed. While for the CPUs, you typically just get throttled. So if you start suddenly using 10 CPUs, well, 10 processes at full time, it will get 0.2 to be throttled. And to finish, one example of a job. So far, all I had was pods. As you see, it's very similar. It adds slightly different header, and you have the option to specify how many tasks inside the pod, inside the job. I mean, how many pods you want to run as part of the job. And you also get an index that tells you which one of the n pods of the specific job you are launching. So you can easily specialize the different jobs based on the index. For example, if you do a parameter scan. So that's how you launch jobs, but you probably will want to do something with them. You need a way to fetch the output. We know that getting the input in is possible natively with Kubernetes with config maps. But there is no equivalent to get the output out. There is no way in Kubernetes to say, stick the output into an object for me to retrieve later. Well, sort of. We have standard output and standard error that can be accessed at any time, and you can fetch it with kubectl logs. That's really standard output and standard error. And you can do it either while the job is the pod is running or after it is terminated, but before it's deleted. The moment you delete the pod, all the logs are gone. The logs are standard output and standard error. If you need anything beyond that, and most applications likely will, you have essentially two options. You either use the persistent storage. If you have mounted it in, you just write it there and it will stay there, or you explicitly copy it out. And this is not managed by Kubernetes. You have to do it yourself, but it's always an option. You will just need to manage your credentials, and depending on the credentials you have, you can use any of the tools like S3, Globus, SCP, you name it. As long as you have the tools inside your image container and the right credentials, it's fair game. So that is all about that you will need to transition from a batch environment to a Kubernetes environment. I believe it's not too different from what you will find in a, let's say, HT Condor-based batch system, apart from the fact that you don't have a shared file system between your submit node and your worker nodes, although nothing prevents you to create a shared file system in your cluster, but it's not a requirement. But apart from that, the syntax is different, but the concepts are very similar. And I'll spend a few more minutes just going beyond what you would typically do in a batch system and see what else you can do in Kubernetes and why people actually have developed Kubernetes in the first place and not just stuck with batch systems. One is networking. Kubernetes manages actively the networking of its environment. Each container, when it starts, it gets its own private IP address. So it allows you to communicate between different containers seamlessly. Just be aware that you get a different new non-deterministic IP every time a pod starts, so you need to have a way to know who to talk to. Now, this can be solved by using something called a service object, and I have a link down there, that will create a permanent network address and a cluster local DNS entry that you can connect to, and this will route the traffic to any of the pods that are attached to it. Who is routed to, it's essentially based on the attributes of the pods and how you define the service. I will go into details. You can read all about it in the link, but be aware that there is such a concept in Kubernetes. However, this doesn't mean that you get incoming connectivity from the WAN. You get typically outgoing connectivity, but there is no way for to connect to your pod directly from, for example, your laptop. However, for debugging purposes or interactive views, you can create a tunnel using the port forwarding, very similar to what SSH does. And again, kubectl is what it does. You do kubectl port forward, and we create a tunnel that you can use to tunnel the data from wherever you run port forward to any pod you own. And again, not more details here, not much details here, but you can read about it at the link. And if you want to do something more fancy, Ingress is very popular for HTTP or HTTPS traffic. It's essentially conceptually a superset of the service, but it works at the application layer, so it allows for much more flexibility. And typically, most clusters have an option to expose that to the outside world. So if you get the right permissions, you can stand up a web server inside your Kubernetes cluster and access it from anywhere in the world. Again, I'm not going to details. This is an advanced topic. You can. I don't have the time. There's the link. Another thing that may be of interest to this crowd is what about MPI jobs? And you may have noticed I have been talking more about high throughput computing than high performance computing here. And that's because Kubernetes does not natively support MPI jobs or gang scheduling in general. It's really optimized for one pod at a time. That doesn't mean that MPI jobs cannot be run, but you need to use some add-ons. And there have been several external projects developed over the years to help facilitate that. The two I'm aware of are Kubeflow and kubeOpenMPI. You have the links there. I can't say which one is better. I know some use one, some use other. It's just not native to Kubernetes, so something to be aware of. But this brings us to the real power of Kubernetes, and this is its rich ecosystem. Kubernetes is actually quite powerful by itself, but personally, I don't think it's better than any of the batch systems I'm aware of. It's really the surrounding ecosystem that makes it so valuable. The Kubernetes have become the default, the de facto industry standard in the past few years. So there are many projects who built on top of it to deliver additional capabilities. So if Kubernetes natively doesn't support something, it's most likely that you will be able to find an external project that does provide the functionality you need. The MPI extensions I mentioned before are one example, but yeah, there is just so much going around Kubernetes that I think makes it a real winner from that point of view. However, if all you need is really just batch system and you don't want to be bothered by YAMLs and pods and stuff like that, it's actually pretty easy to create an proper overlay batch system on top of Kubernetes, because Kubernetes is really a superset of a batch system if we ignore the scheduling capabilities, which I haven't gone into many details, but there are some limitations there. But yeah, it's easy to create the overlay batch system. We have been doing it for with HT Condor in partnership with OSG for many years, and it's pretty simple. If that's the way you want to go, feel free to contact me or anybody on the OSG team, and I'm pretty sure they will be happy to help you with. And that's all I have. So I'll just flash the acknowledgements, but that's it.